In the video.
I know, let's do some math. It's math time. That's Jasper. I'm Adrian. This is the Tutor Wizard. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of others on our channel. We're in Linear Algebra 1. This is Chapter 1, Systems of Linear Equations. We're doing 1.6 Augmented Matrices and Row Operations recap. This lecture, what we're doing is an overview now of what an augmented matrix of a linear n by n system is, and the 3 row operations we're going to use to manipulate that. And then in the next lecture, what we're going to do is talk about Gaussian elimination, which is this process of augmenting the matrix using 3 row operations to turn us into row echelon form, a magic form that we're going to get. And then that will always tell us whether we have one solution, no solution, infinitely many solutions. Let's do it. All right, given a linear n by n system, this is what it looks like. Sometimes we put the curly braces around it to remember that it's a set of m equations, all of which are linear in n unknowns. So the orange index is going to be the row or the equation that you're in. And the blue index at first is going to be what we're going to say the column or the variable that we're talking about. As soon as you have a linear system, what we're now going to train you to do, Pavlovian-like, is augment the matrix. What we've essentially done is just made a rectangular array of a bunch of numbers, and this line is representing the equal sign. And then we've just got rid of all of the unknown variables and all the algebra pluses and minuses, and we're just keeping the coefficients. And this is what we mean by the augmented matrix. If we have to in notation when we're talking about improving stuff, we're going to use this notation. A equals the column vector B, this one. And we specifically call this guy the coefficient matrix because it's the matrix of all coefficients of all these entries. And this guy we're going to call the column vector. Specifically, if we have an example, let's erase this. If I have a specific example, I can cook up an arbitrary linear system now. If I have x1 minus 3x2 plus 5x3 equals 7, I'm just making the numbers up. And then let's give us a second equation. I have 2x1 minus 4x3 equals 5. And then I have x1 plus 2x2 minus 3 or plus 3x3 equals 6. That's how you randomly generate a linear system. That's what it looks like. It's a 3 by 3 linear system because it has 3 equations and 3 unknowns. This is ideally what you want, is a nice square 3 by 3 linear system. From this 3 by 3 linear system, I immediately get an augmented matrix of 1 times x1, negative 3 times x2, 5 times x3 equals 7. And then you can see where we're going with this. 2, 0 times x2, negative 4, 5, 1, 2, 3, 6. Now that I have this, what I want to do with this scenario is take this augmented matrix and use the 3 row operations which we're going to list now and systematically get it to a magic form, which we're going to do in the next video. If we have a linear system which has m equations in n unknowns, we immediately augment the matrix, getting rid of all the algebra, essentially, and just keeping the numbers. When we do an example, remember these are all numbers, they're not aij's. There'll be 3 and a 2 and a 7 and a pi. Numbers at least, not even pi probably. Once we have this beast, what we're allowed to do to this thing is, remember this is row 1, row 2, row m. We're going to have m rows, and we have n plus 1 columns, but let's not worry about that too much. But this is going to be our variable 1, variable 2, and variable n that we're talking about in the system. What we're trying to do with this and why we are going to use these 3 row operations, which we're about to describe, let's describe those first and then I'll get to where I was going with that story. What you're allowed to do to this matrix with these rows is you're allowed to multiply any one of these rows by a non-zero constant. What you do to one side of an equation, you do the other side of the equation. And that's what that looks like in linear algebra now. Row operation 2, you are allowed to interchange any of these as many times as you want. This is a really good operation because I want a leading 1 in the top left corner is my mantra, which is Gauss's. It's mine now. When I want that, if I have a 1 somewhere else, I use this one and I move the 1 to the top. That's what we're going to want to do. You're allowed to do that as many times as you want, interchange rows. That doesn't change our system. And the third thing that we're allowed to do is the third row operation is replace a row with that row added to a multiple of another row. And here's the notation that we're going to use to describe each of those moves so we know what the heck is going on when we try to do this. You can annotate and say, this is what I did, and then I did this, and then I did this. We're going to try and do these things in combination as many times as we want and in any order you want. But the goal of this now is to get it into a nice form to where, here's where I was going with the story now. Our goal is it's going to be called Gaussian elimination after Carl Friedrich Gauss, who invents it first and systematically uses it to find the orbit of Ceres, the largest asteroid in our asteroid belt. What he's doing is, it's called elimination because he's going to get a leading 1 in this top corner. And then he's going to use that to add multiples of that row times whatever other numbers are here. If I have an A21, I'm going to multiply by negative A21. And then when I add A21 minus A21, I'm going to get a 0. And I want to get a 0 below here. And then I want to get zeros all the way down below. And then I'm going to move to the next spot. Without loss of generality, let's hope there's a unique solution, and it'll be this column. Sometimes it's not. You'll see when we get there. If you don't know what I'm talking about, it'll be this guy. And then I'm focused on this guy. My mantra is going to be get a leading 1 there now, and then get zeros all the way below. And what we're doing is we're eliminating the variables. X1 variable will no longer appear. And what it's doing to the system is, if we put a 0 in the matrix, we're getting a 0 here, and it's eliminating that variable from there. And if we do that here, it's eliminated variable x1 from all of the equations except for the first one. Then what we're going to do is move to the next one. Then we're going to make this one a 1, and we're going to get rid of all of the variables in that column. X2 will be gone in all of those ones. And then eventually we'll get down to everybody's 0 except for that last equation. And then I have 1 equation and 1 unknown, and I can solve for that. That will be the unique solution, is BM over whatever that coefficient turns into when we do the row reduction. That is the story of what we're now going to do. We're going to use this beast, these 3 row operations, to put it in a nice form to find out what the unique solution is, or infinitely many solutions, or no solution is every single time. Let's try that out. All right. Example, solve the linear 2x2 system using the augmented matrix and row operations. There isn't one here because I claim 2x2, just give me 1, will immediately within 30 seconds deduce whether we have 1 solution, no solution, or infinitely many solutions. We're going to augment the matrix, row reduce. It only takes a couple steps and we're done. We're in the form I'm looking for. Let's make one up. If you know that I like numbers, you'll see where I'm going with this right away. But this is 2x1 plus 3x2 equals 1. And 5x1 plus 7x2 equals 3. This coefficient matrix is the first 4 prime numbers, 2, 3, 5, 7. I know there's a unique solution because the determinant is -1, so I automatically know that there will be a unique solution, and I have several methods. By the end of chapter 2, we'll have several different methods for tackling this. Right now we have one, which is called augment the matrix and row reduce to row echelon form. You know everything except for that last part of the sentence, which was row echelon form. This is what it's going to look like for a unique solution for a 2x2 system. In the next video, we're going to systematically train ourselves for this. I immediately augment the matrix 2, 3, 1, 5, 7, 3. Also, because I've arbitrarily done this, even though it's not quite arbitrary, I just picked these numbers. There's probably going to be fractions. Don't expect that your solutions are nice integers, even if we get all integers in the matrix. Now what do? The mantra is, and we could work awfully smart or hard right now, so here's a really good thing we want to do. The first mantra you want to train is, I want a 1 in the top left corner. And everyone wants to either divide by 2 or divide by 5, and I'm going to get horrible fractions. That's okay because it's a 2x2 system. I don't have to do too much work. But what's 5 minus 4? 1. So I'm going to create a 1 by doing something weird. If you didn't notice what I'm doing, eventually you can do any row operations you want in any order. There will be a unique reduced row echelon form for a matrix, so it didn't matter, and you didn't have to do exactly the order that I did. As long as you use the 3 operations in the correct order. This is like shearing a sheep. At first I say, what's the goal? Make a hairless sheep. And you're like, I don't know how to do that. So I'm like, here's how you do it. And you grab him and you shear it, and then you get him, and then he's got no hair, and you're like, you're too rough. I don't like the way you do it. It's like, well, if you have an alternate way of shearing that sheep, the goal is hairless sheep. Produce a hairless sheep, I'm happy. You don't, at first you have to mimic me, but the goal is shearing a sheep. What's the sheared sheep here? Row echelon form, so I can tell whether there's 1 solution, no solution, or infinitely many solutions. Eventually, when you know that's the game and you don't like exactly the way I do it your way, but you're only allowed to use 3 rules. I want a 1. I'm going to multiply equation 1 by 2 and then add it to this one to get a 1. Or I'm replacing row 2 with row 2 minus 2 times row 1. What does that produce for me? Another equivalent augmented matrix, which is simpler. somewhat. That gives me, now what I'm doing is multiplying 2 into all of these coordinates and then adding them correspondingly to these guys. So I'm going to get 5 minus 4 is 1. First of all, I didn't change this at all, so I'm just going to copy that row down. Every time for REF, that won't change. 5 minus 4 is 1. 7 minus 6 is 1. And 3 minus 2 is 1. That was actually quite good. I didn't even plan it that way. Now what do? I want a 1 on that top corner. I'm allowed to interchange rows whenever I want, so I'm just literally going to interchange rows 1 and 2. Now I have what I want. Now I have a leading 1 in the top left corner. That's your first goal. I don't care how you do it. That's what you want, because I say that's what you want for now. You'll see why immediately. Why do I want that 1 there? Because now I want this to be 0, so I can eliminate variable x1 from this second equation. How am I going to do that? I need to multiply this by something and then add them so I can make this a 0. If you make it a 1, it's really easy to see. I'm going to multiply by -2 and then add them. Now this time I'll get a 0. So we're going to do the same move. Row 2 goes to row 2 minus 2, row 1 again. But this time now, I'm multiplying the -2 onto all the spots, and what am I going to get? This time I'm going to get 1, 1, 1. 2 minus 2 is 0. That's why I did it. I've now eliminated x1 from that second equation. And then I have 3 minus 2 is 1. And 1 minus 2 is -1. And now everybody forgets this is the magic form we're looking for, called row echelon form. In the next video we're going to explain this in detail, but quickly there's 3 axioms. If you have any non-zero rows, we'll go through all the dry definitions too. But do you have any non-zero rows? I don't have any non-zero rows. If you have any leading entries in any of these non-zero rows, they have to have zeros below them. Okay, check, check. And if you compare any 2 non-zero rows, the row lower has to have its leading entry further to the right than the one on the top. What? Exactly. There's this horrible row echelon form that we're going to do in the next video, and we'll explain this in detail. This is a row echelon form, and I can immediately remember that these are the equations now. This is going to say x1 plus x2 equals 1, and x2 equals -1. Because this is one equation and one unknown, it's already solved for x2, so I know what that is. Now I can put that in here, and I get one equation and one unknown for x1, and I can solve for x1. This immediately tells me that x1 plus -1 equals 1, or move that over, x1 is 2. Therefore, I get the unique solution, which is in general form, x1 equals 2 and x2 equals -1. We want to get a systematic way of using these 3 row operations to get to a nice form. We're going to describe that form in the next video, and then we are going to talk about Gaussian elimination of an augmented matrix to row echelon form to find out whether there's one solution, no solution, infinite many solutions. Please subscribe right here. I'll see you next time.